just put a scale figure in, and this is actually a massive, massive, massive bubble. Just tested it, and we're gonna basically quickly look at how to process the data that we had last time, the UV, W direction, and the mesh, to eventually bring it into a Karamba environment, which will then allow us to do a real-time evaluation of the whole structure itself, including displacements or load scenarios that you may have in different loading conditions. So I'll talk you through all the steps here. But before I'll do that, so there's a few steps that we need to do in terms of file preparation to get the correct layouts that we need. So if I zoom in here, you'll see, I mentioned this briefly last time, is that I added these vertical or normal directional connections between the bamboo pipes to do the to recreate the hinges. So all of that needs to be recreated. You'll also see that the model is faceted, but it's not faceted on the straight lines itself. I made some further subdivisions inside of it. So that's something that we're going to have to quickly prepare with. But let me first talk you through the ZCB Bamboo Pavilion, which is this one here. All right, and how we arrived at that design. Oh, why is it not showing? Why is this not showing? Hold on. One second. Zoom. Okay, here we go. So that's the ZCB Bamboo Pavilion model. You get a sense of scale with that figure in there. So what you see, the curvature is actually quite tight. A lot of the curves are very strongly bent. And if I compare that to the bubble that I just showed, you'll see the bubble is much more relaxed. And it's interesting to see how those differences in forces really play out differently. But let me, hold on, I'm being bothered here. Let me switch off my phone. Yeah. But let me first analyze the model itself that we have. So there's three parts that need to come in. So I have all the curves here. So the first part that needs to come in are the actual beams, which are all of these. And you see they're all nicely offset. And then we have the connections in between them. I'm just going to bake this for a second so that you can see what I've done with the geometry there. This is a lot of trial and error to eventually get to this point. So I'm not going to talk you through every test that we did beforehand. I'm just going to bring you immediately to where what we found out worked for the calculations. So what I've done is each of these members is actually broken up, oh, come on, in tiny segments that define the curvature. So you see all of our lines are interconnected, are broken down into segments. And then the connectors are just straight pieces that go in between them. Actually, let me explode that. That's going to be easier to see if I do it like this. So here you see that all of my curves are broken down into line segments. So here I split into 6, 1, 2, 3, 4, 5, 6. Those make the continuous beams. And then I have to make sure for the connectors, which what you see here, is that those points totally overlap. So we have to eventually get our model into that state. Adding the subdivisions here just adds to the resolution of your calculation. So that's actually a slider that you can work with. And then the way Karamba works is similar to Kangaroo in a way. You have an analysis button here. Again, I'm not a structural engineer. I'm not a Karamba specialist either. I know some of you have more experience there than I do. So if I say something wrong, please just interject and correct me. I'm more than happy to learn from you guys. But where it's similar to Kangaroo is that you define your loading scenarios, your sectional elements, your supports at the bottom, etc. So here in the assemble button, which so these are all, come on, work with me. here. So in the Karamba setup here, you have the analyze button, which sits there in the algorithm. So we're going to work with the small deflections button. I don't know why we're not working with the second or the higher order analysis, but this is the one that the Karamba team recommended us in the end to work with in the past. So here we have all the elements that come in. So every piece of information that goes to our geometry has a unique ID. And if you zoom in here, I don't know if you can see that. And then, so here we have beam, and then you'll see curly brackets with a 0 and then element 0 inside of it. So every beam that we have, every segment has its own number, has its own ID tag that we've extracted from the data structure. I'll show you that in a bit. Then we also have the supports, which are basically the points where it's hitting the ground. Then we're defining the cross sections, which is the material that we give to the elements of our project. And we're going to use the ID, the element ID here, to assign material. So the bamboo will be one, and then the cross sections will get another material. And then we'll also specify the joints that we had before. So as I mentioned in the past, what the idea is that we're basically going to create, if this is a bamboo member and this is one that's crossing it, we're going to put a hinge here, a connector there, and a hinge here. And then actually, if there's a third member coming around, then we're going to have another one and a hinge here. And these are, hinging in all directions. And the element that we have in the middle here, this one, we're going to make that a steel element. Not that it really matters. They're so small, but it's basically just a placeholder as a spacer in between them. They're small, they're tiny, they're adding a little bit of weight to the structure, but it's basically negligible in the overall. It's basically a placeholder that again fits within the philosophy of working with things that work without being hyper precise or being super reflectant of the reality. And then at the bottom here, at the very end, we're going to have our foundations, and our foundations, they'll be locked in all the directions. So let me go over these one by one. So here, in the very beginning, one of the first things that we're going to define here, which is what we have here, is the resolution here, the limit distance for coinciding points. So similar to Kangaroo, as I mentioned, Kangaroo has a tolerance. If 2 points are within a certain range of each other, it will consider them as one. Karamba also does that. It allows you to very easily control that. So in 2 locations here and here, we'll basically use a value that's coming from our design as an input. So what I'm doing here is I'm just measuring all the beam lengths that we have. Let me just look at that here. And then we're sorting them, we're defining the bounds of what we have of all of our numbers. So all my members are between 2 millimeters and 1.6 meters. Although, good point there, although my computer is drawing in millimeters right now, it doesn't matter. Karamba, the millimeter, let's just say that that's the unit. And Karamba works within this unit system and automatically turns this into meters to work with. So we're talking about here from 2 millimeters to 1.6 meters. And then we're going to just take the lowest value. We're going to multiply that with something that is smaller, say 0.9. And that's the value that we're going to work with for the merging. So now we're sure that never a line segment will be smushed down into one point. That's the key idea here. So that's straightforward. So that's the first part. Then we need to give all our elements a name. So here on top, oh, come on. Oh, come on, don't get glitchy. Okay. So here we have all our beams. Currently, they're all, it's each line segment. So each one of these arches is split into 6. So we have we can very easily get the data structure out of it. For this one specifically, we're basically combining the path that we have with the number that the index number that each element has inside of it. So we're basically naming everything beam 0, 0 parts, first part, second part, We're turning that into text, and that's basically the element ID that we're going to give to all of our members. So what's important here is that, we're basically assigning each line with a unique ID. And then, that's that's about it. So that's the basic setup that we have there. Then line to beam, main connections. Let me delete, let me hide this one for a second from here. So the connections that we have are all of these. So here we're not giving them an ID, an individual ID. We're all just going to name them con from connector. So they're all going to have the same ID name, which is fine. They're all the same anyway. And we're going to give those, so we're going to make those little beams. So that's a line to beam button, which is just a modeling tool within Karamba. You can give geometries to each and every one of the beams that you want to have. So here we're going to give those a specific cross section. So within Karamba, you can define the cross sections of the materials that you want to work with. You have all types of sections that you can work with, I-beams, square beams, whatever you want. So in our case, we're just going to make this a little round beam with a diameter of 8 centimeters and a wall thickness of 1 centimeter. So that's just that little placeholder ring that I was talking about. And those are going to become all the metal parts here. Now, the material is standardly set to default steel. So we don't need to add anything there. As I mentioned, it's just a placeholder, and they're not going to affect the load-bearing capacity of the entire pavilion. They're just there to space out the layers. So those are the connectors. Then the foundations. So I'm going to take all the points. Whoop, okay. So we're taking all the points from our design here. And I'm just going to look at which ones fall below a certain Z value, a certain height. And basically that's all of these. Oh, hold on, let me delete this one. That's basically all of these. Come on. All of these here. So these we're going to make the foundational points. You can see here that the model is not super precise. There's a strong subdivision in some of these elements here. It doesn't matter. They're all anchored to the ground at the base here. In principle, this just means that we have a slightly higher locked up foundation here. But basically in the foundation, so these are the points that we're going to make supports. So, oh, sorry, I didn't mention this. So the cross section that we have here, that all just goes into the element ID and to the element ID here. Here we have the supports that become a separate input to the Rhino assembly. And here we can decide in which angles, in which directions we want to lock this in. So we have the translation vectors X, Y, Z, which means that the point cannot move around in space. As I showed you on Monday, our columns are slit over a rebar. So that means that they can definitely not move around in the X, Y, Z direction on the ground. But that rebar actually also locks them into a rotation around all of these actions. If you want to have a hinge on the ground, well, then you just need to switch off your rotations here. Oh, I shouldn't do it because the calculation might take some time. You just switch off your rotations here, and then you basically have a hinging connection on the ground. Sometimes, like some of the details that other bamboo structures have had is where people at the end make kind of a steel gasket or something that sits inside the bamboo pole, and then with the ball joint is connected to the ground. That if you would have that, then you would basically switch off all your rotations. You basically have a bamboo pole that can rotate around. So that's a straightforward. Oh, come on. Clear all drawings, close. Yeah. So that's supports that go in. Then all right, okay. So then the self weight has to go in. So the self weight, that's just again the loading scenario. So we have this In the file that I'll share with you, I've updated the buttons to the recent ones because this file was written with an earlier version of Karamba. But in the loading scenario here you can set up different loads. And there's different types of loads that you can pick from. Gravity, point load, initial strain has been added for us specifically a few years ago. And so the whole pavilion will be subjected to gravity. I mean, the downward vector is just made -1. This should be -0.981 to be fully accurate. But that's basically, the self weight of the entire pavilion. So the bamboo will be will have a material property, a density, and this will automatically calculate it for everything. So that's just a vector that goes in. But here you need to specify in which load cases you want to have your gravity work. So what we did, so in the Hong Kong building code, there's a few scenarios where you need to make sure that your pavilion works. One is, of course, just under normal self-weight, which means that the only loads that you have is basically your gravity working down on everything. Now, in our case, that means gravity plus on top of that, actually the initial strain as well. So that's load case 0. It's gravity plus initial strain. Difficult to write here. And then there's a whole bunch of other load case scenarios that you can get, and that is if the wind comes from north, east, south of west or west, then if the wind comes from the top, which is an abstraction, and then if the wind goes up, which is a suction. So there's basically 6 loading scenarios that we have there to consider as a whole. So the gravity works in all of the load case scenarios. So here, the loading case scenarios have numbers, and this is just a disclaimer of what it means. So load case scenario 0 means self-weight initial strain. Load case scenario 1 means this plus downward wind, upward wind, and then north, east, southwest. So those are the load scenarios that we're working with. And here we're identifying which numbers we want to apply the gravity to. Then we have the initial strain coming in. So initial strain is a similar load case scenario. So it's the same button, just pick initial strain here. We apply it to all the scenarios that we're working with. And here we need to have the curvature kappa in meter -1, so per meter. And then we need to apply the element IDs as well to it. And those are the only 2 values that we need. So we need to calculate the curvature of our pieces. So that's why it's important that the input that is given here in your curve, in your model, is that those are curves, not polylines. Because if you abstract your model to polylines, say, and then you evaluate at parameter 0.5 what your curvature is, for all of these points, your curvature is infinite, right? So you need to make sure that for the Karamba models that you work with a smooth, continuous curvature setup that of course still intersects with all the points that we have here. So we're gonna have to redraw that a little bit. And then you can segment it as if you want to as well. But basically the curvature analysis that you'll do in the middle of each and every one of the segments cannot be or should not be infinite if you wanna have a loading here. So what we do is we evaluate the middle point of our, so here's 0.5, just the middle point of our curve. And what that gives you, so this is a standard curvature analysis button that you'll find in Grasshopper. So that gives you the evaluation point. It gives you the curvature vector at a particular point. So that's basically the, if I say this correctly, this is our curve. Let's say that that's the tangential circle here in the middle. The curvature vector is basically, yeah, this one that goes all the way to the end. So then all we have, so it's basically the radius of the tangential circle that is tangent to that parameter t that we're looking at here. So that gives us the how much your pipes are being bent, basically. So then all we need to do is, yeah, get the length of that vector, because the orientation doesn't really matter. And then we're turning that just into a y vector with that same value, because the orientation of this curvature is done relative to the XYZ coordinate of the elements themselves. So each element that's brought in has its own orientation inside the Karamba calculation. And this is just, so let me sketch that out again. Let me sketch that out. If we have a curved member like that, that basically becomes its own X, Y, and then Z plane. And basically, so that's X, that's Y, that's Z. So we're just making this into a vector in the Y direction that then defines how much curvature we have. All right, so that's why we're bringing this down into a Y plane. And let me quickly double check something, because somewhere, at one point, yeah. So here, that's why this value K here is connected to the Z value here. So that's basically where we orientate the beams, as I was mentioning here. So we're making sure that the, I don't know why it's going to Z and not to Y. This is something that Clemens Preisinger, the author of Karamba, did for us. It basically means that we're making sure that the orientation is done correctly. I don't know the full details there. But that's it basically. So we're defining the bending or the curvature that we have there. We're assigning it to a particular element for a particular load case scenario. Then on top of, so we now have self-weight, gravity, we have the initial strain. Then we also need to add the wind loads to it. So here, this is again a different type of load that we can give. So for the wind load, we're going to work with the mesh. That's why it's essential that we have the membrane. And basically, yeah, it's a standard tool that will just look at the surface area of your object in, so if I would look at this one in front view, yeah, it will basically look at the area here and we'll put a pressing force in that direction, and here it might put a suction force in that direction. So it's just analyzing your mesh. The resolution of it does not really matter as far as I can tell. But let me just show you how we go about it. So we take our mesh in from here. And then, yeah, here we've still subdivided it further to make sure that we have a totally smooth mesh. So let me quickly use Weaverbird to show you the density. Not that that matters too much, but we're calculating with a very, very, very fine mesh here. It doesn't really increase the calculation time, just gives a slightly more precise calculation, I guess. Here we need to have the input surface loads for that basically define the load distribution. And again, we have we have, in this case, the first load case scenario that I mentioned earlier, self-weight initial strain, does not require wind. So we have only 5 scenarios where we have wind, 1, 2, 3, 4, 5. Of course, Grasshopper starts to count at 0. So the first wind here is actually self-weight and is actually a downward wind that we'll be using. The second one isn't, so that's why we're going in a minus Z direction. Second one is an upward wind. And here you see in the Hong Kong building code, that's where they specify that we only need to work with 2.05. Is it Newton per square meter or kilonewton per square meter? I'm actually, kilonewton per square meter. That goes in. And in Hong Kong's building code for temporary pavilions, we can work with a reduction factor of 0.41 because this is calculating, otherwise you're calculating with the 5-year storm, and this is calculating with 100-year storm or something like that. So that's why we have a reduction value. But for uplift, there's another factor of 1.4 that needs to be calculated in, because that's of course really dangerous. Like if your pavilion would actually lift off and take off and move itself. So that's why there's another safety factor in. These are all just values that are coming in from the building code. So downward wind, upward wind, and then north, east, south, and western winds. These are brought in, and we have to assign the load cases where these are assigned to. So the first one goes into load case 1, the last one goes into load case 6. Nothing too special. The orientation here is global. That's important, so that we're basically using the north direction that we have. And then generation, I don't know the details there, but we're generating point loads and line loads on anything that's surrounding it. So that's the load. Those 3 are the loads that are coming into our assembly button here that brings in all the data for the model to analyze. And then the last things that we still need to define are the joints. So the joints, so this is for the connectors, the little metal pieces that go in between it. You see we're applying it only to the elements that are named con, which are the connectors. This is actually written with double N. These are the connectors that I have specified over here. So on all of those connectors, yeah, we need to give it a spring stiffness. I don't know why it's set to 10, but this works. We're basically making it free in the X, Y, and Z direction so they can just rotate freely, basically. Translations are not constrained, which means that that element can move around in any direction freely, and then the rotation is constrained with the neighboring elements. Then, so that's the setup for everything but the bamboo. Then the last part is the bamboo itself. So there's two things that we need to do. We need to specify the material, and then we need to specify the geometry that we have. And we're applying this to every element with the element ID that I defined here in the very beginning. So every bamboo element is going to be given these material properties. So that's where the IDs matter. Currently, we're setting this to round sections. Note that there's no setup for diaphragms in between it. So this is again an abstraction of what bamboo really is in reality. Note that it's also working with a constant section. This is also an abstraction of going from thick to thin. But right now we've just set this to a pole of 9.5 centimeter diameter, because in reality our poles would go somewhere between 7 and 12 centimeters, the ones that we're working with. So we just took an average there. We're also again taking it an average wall thickness. So yeah, this is one of the. Let me quickly show that. So wall thicknesses can differ quite a bit. Depending on where you are. So this is again just an average that we've taken for the whole setup. But you'll see that the outer diameter matters much more than the wall thickness, because the initial strain that you get responds to the diameter of the pole more than anything else. What I showed you 3 days ago with some of the graphs. A thin stick is much easier to bend than a big stick, basically. So the bigger the diameter, the higher the initial strain is. And then you need to apply your material properties here. So standardly, you would get metal, but we need to override that. And here we have an example of the bamboo that we have worked with. So, which is called Philostachys pubescens. There's different values in the literature. I'll show you that in a bit. Yeah, and you're basically applying the Young modulus, the shear modulus, and the transverse shear modulus, and the elasticity modulus here in these two directions. Then here you also define its self-weight, kilograms per cubic meter, and then the yield strength that the bamboo has. And then, yeah, the material type, this isn't abstraction again. We're just saying that this is an isotropic material. So you can see quite a few abstractions that have taken place also here with the safety factors. And that's basically the whole setup that you have. I'm going to give you this as whole, so that in principle, the only thing that you need to do is produce your input parameters the way that we had it here, and then the system will automatically calculate it for you. So let me keep going then here. So here we have the assembly button and the analysis button. What's coming out of that is you can view your model. Let me delete that for a second. Let me switch this off.
Son los compañeros. Ella es Camila, es de Brasil.
Yeah. Switch these off.
Ellos son de, ahí los sigo en Instagram. Todos son de otros países.
So you can, for example, do a beam view. Put this in perspective. Oh, okay, that's not working. That's the person that we have there. So here you see the stress analysis in place. And you'll see that in this case, if I look at load case scenario 5, which is with the southwestern wind, that we're utilizing our material beyond its capacity. We're going over 100%. We made this little graph here, this color graph that allowed, if you just bring this in, then it will only show you where it's actually failing. So it's failing in blue here. So it's overstressed in some of the corners here, tension on the outside, compression on the inside. And then you'll see in some of the foundations, a little bit of cracking happening in the model, but that's negligible. So this actually shows us that in the normal load case scenarios, it would break there, which is what happened on site. Here we had to nudge our bamboo poles and artificially bend them to make it work. Let me bring it back to the original color scheme that they have. Oh, come on. So here you get a better overview of all the colors. And then you can change your load cases. So in load case 0, only its own weight, you'll see that it's still the same thing. Even in the only its own weight, we're over the extremes of what we can do. If you look at the uplift, so that's case 2. There, yeah, changes a little bit, like we're dropping the numbers a little bit. Yeah, we're changing it a little bit, but we're not really changing much there. Nice thing is you can also visualize other things like your displacement, for example. So, come on, let go. So this model here shows a displacement, which is quite interesting. It actually shows that the parts of our model that are moving the most are the belly area. And I didn't explain this in detail in the in the lecture that I gave you on Monday. But we actually added a metal wire that would connect all the middle points of these big overhangs, and we suspended that from the arch above. So the upper part is close to a parabolic arch, which is ideal in compression. And we actually pulled up like this point here, for example, from a point above it, this point from a point above it, this point from a point above it. In response to that, this is something that we observed in some of the physical models, actually, that these points were the weakest. So we had, before we even knew this from calculations, we had already fixed that. So yeah, that's a fun visualization tool. This is now an uplift. Let's see if we look at downward wind, and then it's probably going to be even more. So now you see again that the top part hardly moves, but that the belly area is where this design was quite floppy. Yeah, so that's pretty much it. I mean, you can visualize all kinds of things like your resulting forces in the foundations. As I mentioned, this is another Caramba course per se, but there's quite a few pieces of information that you can extract from all of this. Yeah, but this is kind of the basic setup that we've been working with in the end. Any questions or comments? Because then I'll shift to the bubble structure to get there. Any questions or comments from anybody?
Hi, Crystal. I want to know if how would you integrate the bracing system in this?
The diagonals?
Yeah.
Well, this is a fully triangulated structure.
Okay.
Already, so this one already has its bracing embedded in it. I'll show you in a bit. Let me just load it. I have it here. So with the pop-up grids on the same scale, with the same bamboo settings, this is a bubble that yeah, is a massive bubble. Actually, it's probably way too big. But with the same loading conditions, the same scenarios, it actually shows that this structure works perfectly, or should totally be possible, which is mind-boggling. That actually, if you would push it to the limits of what a material can do, that a structure like this would be no problem at all to build with 12 centimeter bamboo poles. I think this is probably in the range of the scale of the Mannheim Multihalle as well. So it's very interesting to see that if your initial strain, if your bending is very minimal, that you can very easily still reach this. Any questions on the Caramba setup first? Because then I'll go through the grasshopper part. Or any comments from the Caramba specialists? I know there's a few people in the room that know it better, or that may have more experience with it than I do. All good? Hold on, let me open the chat. Oh, I hadn't seen the chat yet. Okay, Enrique mentions on finite element analysis, I understand that for shell analysis, nonlinear analysis should be used with dynamic algorithms to calculate the scissor displacement that are generated in crossing and support. Unlike the linear analysis, there is no longer a proportionality, and depending on the forces are directly proportional to the displacement. Enrique, if you're here, can you elaborate a little bit on how you think that would change the outcome? Because we have tried with some of the different, where are we? evaluation tools here, but we always ended up in facing difficulties with it. Enrique, are you here? Not anymore. Okay, let's see. Maybe later on, if you can. I'm definitely curious to hear more about what your comment is about. Okay, let me bring in, now that everybody's here, let me share the Grasshopper file as well so that we can all look at it together. I'll immediately show you the last one that includes Caramba. As mentioned on Wednesday, Caramba, the trial version, only allows you for like, I don't know, 50 beam calculations or 20 or something. So it's probably not going to run unless you have a working analysis tool. But we can talk through the setup that we have. So it's actually all pretty basic Grasshopper from that point. So this is where we ended up last time, where we had the U direction and we had the mesh. So let me first prepare everything there. So I'll start with the U direction, the UV direction and the diagonals that we had over here. So these are currently all going through the same points. Let me first do the mesh. This is the mesh that I just trimmed based on wait, why is this so dirty? Interesting, something happened in my mesh split. Hold on, I split my mesh based on a plane. So I used the mesh split tool, which basically cuts the top mesh based on that mesh over there. And oh no, maybe it's just a graphic glitch. Yeah, it's just a graphic glitch. So I'm basically just splitting my top mesh based on a large plane that's on my ground plane, and then I'm only taking up the upper part of that mesh to calculate with. So that's a very straightforward part here. Mesh split. Then the curves above, that's a little bit more tricky, maybe not. So I just split them up into two nice directions, the U and the V direction, which I didn't have before. And then I have the W direction here. And as you remember from last time, I have this little switch here that allows me to, what did I do? Okay, that allows me to switch between, come on. Oh, I think my Caramba is still live, so let me switch that off, because otherwise it's going to keep on calculating the whole time. Yeah, that's what's the delay. So this button allows me to quickly switch between diagonal directions that I want to work with. And you'll see that for a bubble structure, it doesn't really matter. There will always be a part where it doesn't fully work well, where you have like these little end parts that are not connected. So that's where you can refine your design manually at the end as well. Anyway, we have our UVW direction nicely lined up over here. Let me switch all of this off. And then the first thing that we need to do is we need to offset those. So what I'm going to do, my U direction will be the base layer. That will be the U direction. And then I'm going to offset my V direction inwards. And then I'm going to put my W direction underneath it. And my mesh will basically be, as an abstraction, my mesh will basically be running through the axis line of my U plane, right? I mean, this is all having a little bit of impact on the final calculations, but this is the closest to reality. I mean, I could even offset my mesh a little bit if I would want to move that above here, but that won't have a very big impact. So the abstraction that I'm doing is I'm gonna, let me start here. My U direction remains, no problem there. My V direction, I'll look at all my line segments as I did last time. I'll look which face for my mesh that I have is the closest to it. And then I'll use the normal from that face to basically move my points down, and I'll recreate my line segments like that. And then here, yeah, this is similar to what I showed you yesterday, actually. I'm redrawing. So from these line segments, which are all faceted, so they're not, sorry, they're not fully connecting right now. Here, I'm just taking one of the points and I'm redrawing my continuous polyline through it. So this is very similar to what I did yesterday. So that's going down 1. There we see that. And then for the W, I'm doing exactly the same thing, only this time I'm making my diameter twice my stick thickness that I have. So currently, oh, I see, actually I made according to my calculation, there's a mistake in the file. This stick diameter should actually be the same as my bamboo diameter that I put in over here. So let me increase that to 9.5. That will give us a cleaner model as well. 10. Let's say that our stick poles go up to 20. I will, oh, minimum 0. I will put this one at 9.5. Okay. Ooh. What's happening here? Oh, this one is in meters and the other one is in centimeters. That's why. Okay. 2. I'll make this one 2. I will make this one 0.095. This needs to be 3. Yeah, that should make more sense. Let me just quickly double check in my visualization at the end in Caramba if that actually is correct. Oh shoot, what did I do? Okay, somewhere my model is not working 100% anymore. Let me undo this. I'm not gonna mess with it at this point. Let me reopen this one. And it's all a little bit delicate sometimes, because right now at the perimeter of our beam, of our shell, it's possible that some of the points start to end up in different layers. Let me see. Yeah, it looks like we're a little bit too thick in terms of our offset here. I'm not going to change it right now, but definitely there's a need of calibration there. So this 0.2 is not correct. Let me see what happens if I make this one 0.095. It might crash the Caramba if somewhere somehow there's a bug coming in. Is it still going to do it? Oh, sorry, it's in the other direction I need to go. That makes sense. 0.095. There we go. And now it's not working anymore. I don't know why. Okay. It must be that somewhere 2 points are getting too close or things are merging. Let's not worry about that for now. I mean, that's all fine-tuning and calibrating and debugging of the whole script. So anyway, so the W direction is just being offset twice that amount. So that's what we're getting over here then. So now I can look at my 3 lines that I have in my original model. So if you would bring this into a structural analysis tool like Robot or something like that, where you want to study this as if it would be a space frame with fixed hinges, then this is the axis model that you would need. And then the offset version of it is actually this one here that we have. Then we need to produce, we need to turn this into NURBS curves as well. So what I've done here is I'm just taking all my line segments, and here I make a division button to divide them into as many as I want, 2 or 3 or 4, depending on what the resolution is that you want to have for your, 6 is probably a bit too high, for your Caramba model at the end. And then I'm just shattering NURBS curves running through it. So right now I should have totally smooth NURBS curves running through it, through these points that I mentioned. So I'm getting my polyline points here. I'm first starting by drawing a NURBS curve through it, and then I'm just shattering each segment into smaller parts. Nothing too difficult there. Then I need to make my connectors. So my connectors, because I have my original layer here and my final layer afterwards, it's just a matter of extracting the right vector points and adding those in, and then adding those in as well. So yeah, it's a little bit tricky sometimes in identifying, definitely for the diagonals, which points to go to, because sometimes, yeah, let me just, I added this button here because in one part I was starting to see some glitches. Like here, some of the curves were, like this curve was actually snapping to a neighboring point. So there's some dirty scripting that needs to be happening to make sure that all your diagonals are nice and clean. But yeah, this is one way to get it nice and clean. And then this is basically where we are with all the data that I have. So I made a very simple data structure at the very end where on layer 1, 2, 3, we have our UVW direction. 4, 5, we have our connectors in between it. And then 6, we have our mesh. And then this is just something that you plug directly into Karamba, and there you have it. So with that concept, you should be able to do that with your shells, whatever you're designing as well. But as I mentioned, each design will create some glitches. Like for example, maybe it's on the other side, I think. Here in this one, like for some weird reason, my NURBS curve are starting to get messy here. So there's something that's not working perfectly clean there because I'm cutting right at the edge. Here, there's a little part where we have free hanging members. That doesn't make sense either. So if you were to go to a proposal that you want to implement, these lines that I've baked in here or put into the scripts, that would be where you would bake your geometry, fine tune it, and then bring it back in. And the challenge of baking your geometry and bringing it back in is maintaining your data structure. But as I mentioned, with tools like, but you can either bake it to different layers, which makes it easy for you to do, but you can also bake attributes to your geometries with plugins like Elefront, for example, to give each object an ID, like a name, and then that name you can embed its data structure, for example. Then you can extract the name again, deconcatenate the text, and reassign it to a particular data structure that you want to have. So this is as close to a fully automated script that you may want to go, but in reality, you would start to clean up things more and have things make a little bit more sense here and there. But then with this in place, if I look at my structure as a whole, this, yeah, kind of works, but it's hardly using any material strains, as you can see if I switch this off. So this is here. So right now I'm using an absolute visualizer. If I use a relative visualizer, you'll see that actually I'm currently getting my extreme strains in some areas where my geometry is wrong, rather than in the areas where my actual structural analysis is would matter. So 0 to 1, 0. Yeah. Yeah. So this actually shows that my structure in principle would work. One last thing that we added here in the bottom file here at the bottom, you'll see some different material values for different bamboo species, like 5 years old, 3 years old. So we've looked into the literature and we found a few different values for the same bamboo species, or even different bamboo species that you may want to have. So if you want to work with local species, you just need the elasticity modulus, a Young modulus, and then the yield strength of your bamboo. And then with that, in principle, you should be able to pop it up. But now, a major conclusion that we drew from this analysis tool is that actually the bending is by far more restrictive in terms of design than wind loads. the initial strain that you get from bending your material very, very quickly outweighs your wind loads that you have, which means that for the designs like anything that looks like some of these that I showed you earlier, like a structure with columns underneath it, the singularities is where it becomes absolutely challenging to materialize these things. Because in the flatter parts of the grids, or in the gentle bubbly parts of the grids, there the bamboo can perform really well. But around the singularities, that's where you need to change things. And what you would change there is what I mentioned earlier, is maybe going for thinner diameters, or going for splits, or going for bundles. Because from the calculations that we have visualized here, which is very clear in the ZCB Bamboo Pavilion, for example, for all the loading scenarios, it's primarily there that the bamboo will start to fail. So there's actually this is actually an argument against working with singularities, or against changing the designs to the degree that we have with bamboo as a material. But yeah, if you can find a way to get rid of the shear forces there, then there's no problem. So to wrap up the kind of conclusions there, I mean, this whole calculation system and design system is now, it's not really about bamboo. It's about bending active shell structures and analyzing them and evaluating them. If you want to work like with the church, the temporary church that I showed you on Wednesday, if you want to work with glass fiber reinforced polymer pipes, which are equally cheap, details with swivel shackles, which are equally easy, you can use the exact same tool and just put in the numbers and see where you are. You can combine different materials with each other. You can go to carbon fiber reinforced polymers, and theoretically you should be able to make massive, massive structures with just that. So yeah, this is kind of that's kind of where I want to end the type of tutorials that I'm going to share with you guys at this point. From then onwards, all the other work that we have done is pure geometry based, like trying to optimize the sorting so that you can remove some manual steps in there. But again, that's more time saving than anything else. Splitting up your Rhino files so that your geometry files, so that around singularities, you can automatically give it a different element ID and work with different materials. So that's something that we're still working on. But yeah, this is basically the point where we are at this point within the research unit over here. Any questions from anybody on any of this? Or comments? Or challenges? Or anything? Enrique, I see that you're back. Would you maybe mind elaborating a bit on your comments? Because I'm very curious about, because we have discussed with the Karamba people at one point in time, whether or not we should use this analysis tool or something, or a higher order analysis. Can you elaborate a little bit? I'm not a structural engineer by background, so I don't know the full details there. Enrique, are you there? I see you're back, but maybe you can't talk at the moment. Okay, if you're not able to join now, then no problem. Any questions or any comments from anybody else on any of these things at this point? No?
Sorry, I still have like a question about the bracing system. So in this case, you've used the third direction again as like a bamboo pole. So would you consider using like a cable bracing or something for the bamboo structures in general?
For the diagonals, you mean?
Yeah.
Yes, definitely. I mean, from my understanding, Karamba has difficulties with calculating cables. Mm-hmm. It's a rod-based system, which is a pity, because in principle it just means that if an element is under compression, it would need to be removed from the equation. Mm-hmm. I don't know if Karamba has updated that in the past year, which was since the last time that we spoke with them about this. But cables would be great to add because they're easy, they're straightforward. From a cost perspective, they might even be, if they're locally available, it kind of fits in the building complexity agenda as well. If you can bring them in, if it's steel, in principle, that's environmentally sustainable, not in its manufacture, but at least it will rust away, or it's more recyclable. So yes, that can work. I mean, the biggest difficulty there then is how do you fix it? Because let's say in this drawing here on the screen that all the blue ones would be steel cables instead, which would make sense for a design like that. Then in a connection like over here, what you can do is if you have your two bamboo columns crossing, say like this, what you can do is kind of fix an eyelet underneath it and tie that to the bamboo, and then have your steel cable kind of running through that. But this becomes a sliding eyelet. And that would, ideally, it would become a sliding eyelet, because then you can guarantee that you have tension throughout your entire system here. What you need to prevent is that the metal will cut through the bamboo, or would make it collapse, or even just from the general motion or the movement of the pavilion, that it doesn't start to saw through it. So that's why working with an eyelet like this could work really well. And then at the very end, you add your typical like tension system to kind of tighten up your cables like that. That could theoretically work. But then to identify how much you need to tighten everything is always a challenge. But what I would do on site with a system like that is we would install the cables, and then we just tension everything. And then you have these tools that allow you to measure how much tension you put on a cable, and we put everything under a light pre-tension, for example. But the challenge is, how do you go about it? Because the minute you start to pre-tension one, you're deforming your bubble. So you have to very gradually first install all of them without tension, then a little bit of tension everywhere, and a little bit of tension everywhere, and constantly be aware of the behavior of the structure that you have. But steel cables could work very well. Bamboo in principle as well, because that can take compression and tension.
And like ideally you'll have to give it for this. I mean, like at like all the grids that you've given in this case.
Yeah.
Like you can't really like avoid certain grids, and then ideally you should give it for all the diagonals.
Say that again.
So like every square you have, do you have to give it at the regular interval, the diagonals, or you can skip like 2, 3?
Well, similar in Friotto's structure, he had a diagonal every 10 or every 20 square units. They will become tension lines inside. A good way to describe it is if you blow up a balloon and you put it inside a very fine mesh, then you'll see that the balloon surface, like if this, hold on, let me draw something. If this is the fine mesh that we have, and you put this, you inflate a balloon inside that, then the balloon will take a shape like that, right? If you work with a much bigger mesh, say something like that, then the balloon will take a shape like that. I think that kind of is and then it will go to the next one and the next one. I think that's kind of a good graphic explanation of how the load impact of your diagonals will work. If you do it on every intersection point of your structure, then your overall membrane is going to work pretty uniformly as a continuous shell. If you do it only on every fifth one, then you do risk having load concentrations in the points that are associated just with where the metal wire is going through. And those load concentrations can over time become points of weaknesses. But that's a balancing act that you would have to do with engineers with proper analysis tools, I would guess. If you're doing it more intuitively, then I would just make sure that you don't make it too sparse, because without the diagonals there, the structure is much more wobbly. Actually, hold on. Oh, maybe that's something that I can. Hold on. My phone is ringing. I don't know if I can cancel this. What we can quickly do. Let me try something. Not in this one, but in the other one, I can maybe switch off my diagonals and see what happens.
Sorry, hello.
Oh. Sorry, hold on. So here we are. Where's my structure? Where is my structure? Oh. So we're just looking at the displacements here. And let me see what happens if I switch off my diagonals, which are the W direction, which is this one here. And normally, I mean, yeah, the displacement is set to relative. So hold on, let me visualize it like this. Maybe this will work better. So right now my highest displacement is over there. And let me enable that again. Okay, my highest displacement is still there, but hold on. I have the numbers calculated here. Go from group. Let me have a look. So currently my displacement range, in one part is going up to 2 meters. That's quite a bit. But I don't know if that's hold on. Well, let's just leave it like this for a second and let me switch it on and off again. See how much that changes if I switch it off. That's funny. There must be a calculation mistake because it's saying that right now it's uniformly 62.6 everywhere. That doesn't make sense. But yeah, in principle, you should be able to calculate this. Yeah, there must be a mistake somewhere. I don't know how the displacement is being calculated here. So something is up. Something is up in the whole setup. But yeah, in principle, the diagonals, you should be able to see very quickly how this impacts the overall design structure.
Okay.
Other question in the chat. I'm not sure how Bamboo is defining Karamba as a heterogeneous material or heterogeneous material. Right now, we just made an isotropic material, which means the same directions, the same properties in all directions. I don't know how to do it differently in Karamba. Theoretically, that should be done. I mean, theoretically, the nodes should even be included in the whole setup. And I mean, that's where we're pushing against the limitations of what is sensical and what's not, and what is required by law, and what is in terms of building codes, and what is practically feasible on site. You know, to fully engineer a structure like this, exactly like you would be able to do with a steel structure, is never going to be possible. You're never going to be able to fully reflect all the properties of bamboo. But maybe because every species has such a wide range in its values. And somebody emailed yesterday that Inbar has just released its ISO standards for the low-rise bamboo column-based architectural projects last week. So that's correct. I think last week or 2 weeks ago, the first ISO what's that called? Building code has been released for small-scale bamboo structures working with solid column structures. I haven't had a chance to look through it yet, but it'll be interesting to see what the properties are that they require for the calculations there. But there will always be this fight between a fully predictable material like steel and an unpredictable, naturally varying material like bamboo. And the question here is, how much control do you need to have in order to be confident enough to build? My attitude there would be is use tools like this approximatively to think about to estimate whether or not something is possible. Then once you build, say, this dome, which is massive, like if I were to build this dome, I imagine Fraiotto built the Mannheim Multihalle without any of these calculation tools. Like, what did he use to decide to go ahead with it? It's definitely a ballsy move, but they, before they made the Mannheim Multihalle, they started with a smaller scale mock-up where, and I spoke at one point, this is interesting, I spoke at one point with an engineer who worked on that with Fraiotto back in the 70s, 80s, and what they did is if you take a bubble shape like this, and you put the point load on it, then you'll see when it starts to buckle. You can know exactly at which point in time it starts to buckle. And then if you add another load on it, you'll know exactly at which point in time it starts to buckle. And I forgot the details, but what he mentioned is that you could somehow take your graph and identify at which loads or at which points in time the system would buckle. And then eventually they would be able to extrapolate from these study models how the complete shell would buckle under total live load. So what they would do on site for this is they would first they would of course calculate and test it ahead of time on small scale models, but then once it's built, they would take a few points here, add water or weights on it to see when the shell goes from a bubble like this to something that buckles in. And the values that they had from that local failing would then allow them to extrapolate it to the whole shell. It's again very, very approximative, but they use these rules of thumb and experiments to come as close to as possible as they could to predicting the actual behavior of the whole shell structure. And then of course you work with a safety factor of a lot. Like in our case here, I mentioned in the wind loads already that there's quite a big safety factor embedded in the types of wind loads that you're working with. And then in the material properties, there's also maybe safety factor built in. Yeah, that's where you do need to have some specialists on board to talk about this in more detail, which I am not. So the goal is for this to become an architectural design tool that gives you the infrastructure to allow to have that conversation. Like if you want to have a conversation with a special engineer, he'll ask for the access model. He'll ask for something like this where you have your hinges signed up. So I would say this is a conversation starter, definitely not a conversation ender. But maybe if you want to go into Bali or Indonesia or Vietnam or maybe India, where there's a different building culture than what we have here in Hong Kong, where everything needs to be double, triple checked by the building department and by the insurance agencies and by everybody in place, then yeah, bigger things are possible. I mean, if you look at what people have been building with bamboo for centuries without any of these tools, it's quite amazing, and nobody was freaking out over what they were doing back then. So this is about creating a toolbox that allows you to have a communication with the natural materials that you're working with in a more informed way. We would still work with physical models to test this ahead of time. We would still work with load tests on site to see if something works. So it's maybe a very unscientific way of doing things. It's just an empirical way of doing it. It's an empirical approach. And then the questions come from these tests. Any other points? Any other question? Yeah, go ahead, Islam.
Yeah. In the final model, I saw it was covered by a tensile membrane.
Yeah.
So does it play a structural role in the model?
So in the digital model here, in the calculation model, no. But on site, it would. Because that depends entirely on how frequently you fix it to the bamboo structure itself and how tight you fix it to the bamboo structure itself. Like I know with a steel structure, for example, if you put a high tension membrane on top of it, then the membrane itself can maybe help absorb some of the tensions. But I think that's a rather theoretical thing.
And also it can distribute the bending forces uniformly around the bamboo structure.
Yes, it can. But so there's two reasons why we didn't incorporate that at this point in time. One, we just didn't have the setup to do it yet. But from an argument's perspective, why we didn't go in that avenue is that the structure becomes stronger if the fabric operates as a load carrying and load distributing element in the structure. So by not having it do that, the structure is again a little bit weaker than what it would be in reality. So it's safer not to calculate it than by not incorporating it. It's a safety factor that you're embedding in the setup. But you're correct that in principle it would help.
But it can affect the uplift load because it closes all the structure perforation, so the uplift load will increase.
Well, in the current calculation model here, the uplift load is entirely based just on the area of the mesh, as if it is connected everywhere to the bamboo structures underneath it. So the mesh is directly affecting the loading, but it's not helping in the structural response.
Okay, thank you.
Yeah. Other points? But good points. Very good point.
Thank you so much.
Okay, well then it's 10 to 11 here now. Let's maybe take a 15-minute break until 5 past 11, and then it would be nice if you can maybe share some of your experiments. If you've done any, I hope you have had a chance to look at that. Maybe we can quickly talk about it, and we can see based on those if we what we can maybe make as a poster for Digital Futures, which is what they were asking for, or even a video. So let's make it a little bit more tutorial based afterwards. Okay, Adon. Enrique, you just mentioned something in here. Yes. Great, yes. So Enrique is commenting on how to make the anisotropic or the bamboo materials. Yes, so yeah, you can read the text there. Enrique, can you maybe say something a little bit about your earlier comments about the dynamic algorithms to calculate the scissor displacement width? Would you mind, or can you? If you know Karamba well, do you think it would be possible to do that type of calculation within a Karamba environment? Okay, maybe Enrique cannot talk. Maybe he's in office or something. Okay, all right, no worries. Let's meet back at 11:05 Hong Kong time here in 15 minutes, and then we can continue. All right, see you then.